Hi, Abhishek.
Hello. Sorry, I was actually having some network issue at my end, so it took me a moment to connect back to Zoom.
Okay, that's fine. I can hear you now.
Started the meeting using my phone because my home internet was not working somehow. So, but it
yes, something would look fishy.
Yeah. So I was almost panicking that what is going on. So let me just quickly share my screen and I'll get started. So I hope my screen is visible now.
I can see it.
Great. So I'll get you started. Okay. Sorry. Yeah. So very good evening to all the participants who have joined in from India, and very early good morning to Dr. Rajneesh and anybody else who is joining from US. So we have two very nice talks in this last session of this two-day event. That is the event on latest trends in VTOL technologies, which we are having since yesterday. So the first speaker is Dr. Rajneesh from Army Research Lab, USA. So Dr. Rajneesh is an aerospace engineer who is leading a team focused on basic and applied research in rotary wing platform technologies at the US Army Research Lab, ARL. This includes design, aeromechanics, acoustics, and flight mechanics principles. Prior to joining ARL in November of 2009, Dr. Singh worked for about 10 years as aerodynamicist at the General Motors Tech Center in Michigan. He has a PhD from University of Maryland and a bachelor's degree from IIT Kanpur. So it's a warm welcome to Dr. Rajneesh from IIT Kanpur, his alma mater. He's a member of the board of directors of the Vertical Flight Society and associate fellow of the American Institute of Aeronautics and Astronautics. His research interests include high performance computing, rotary wing aeromechanics, computational aeroacoustics, and VTOL design. So I'll stop sharing and I'll now request Dr. Rajneesh to share his presentation and get started with the talk.
All right, thank you, Abhishek. Thank you not just for the invite, but also for organizing this event. It's extremely timely and I believe very...
Yesterday, actually, we had Anubhav talk about Mars helicopter, which was really exciting. And then we also had Srikanth talk about vision-based systems, which was really nice. So we had a really good discussion and a lot of questions actually came from students.
Yes, I could attend both of those. So, and obviously I do interact with Anubhav quite a bit. And so yes, it has been going really well so far. So let's hope to continue the trend and let me start my presentation. So do you see my slides?
Yes, it is visible. Yes, please go ahead.
And do you see in slideshow mode? Really not.
Not yet.
How about now?
No, it is still showing the slide view mode actually.
I think you can stop sharing, put it in slide view, and then again start sharing.
Otherwise, I mean, you have to do that, share the entire screen instead of just sharing the application. So that works.
Okay,
sometimes.
let's do that. So what did you say, Anubhav? So start in slideshow and then start sharing?
Yes.
Right.
Or I'll just share the entire screen, I guess.
Yeah, that also should work actually fine.
How about now? Problem could be I have two screens here. So let me just take out one of the screens.
Oh, yeah. The two screen thing, I mean, to actually go to the other screen probably.
Yeah.
All
right, so let's start. So thank you, Abhishek. And so again, thank you again for organizing as well as inviting me. And so my topic for today's presentation is design challenges for next generation VTOL UAV. So when we talk about design, mechanical design, this is the classical definition, is process of selecting shape, size, arrangements of different components. So now there are two extremes to it. On one side, we have this so-called jugaad kind of designs. You take things together, put them together, and you have things that work for you. So, and it's not just an Indian concept. I mean, if you see this Oxford driving on the right side, it is a fairly global phenomena. And that does get the thing done, but it does leave out a few things that you would probably want to be better. And then another extreme is this so-called, well, not so-called, the way things are done in Formula One car racing. And I do have some experience of working in racing industry, so I can tell you with the full confidence that each part that you see on this car has been designed with extensive analysis, extensive internal tests, and so on. And then the result shows in the performance that you get out of these. So presentation today for me is really about what are the challenges in creating this Formula One approach to UAV design. And we'll understand with that goal in mind, here is the presentation plan. So from VTOL UAV design perspective, what is exactly what we want out of these? Why are they so difficult to get? What is the underlying science which is preventing us getting it? And then what are we doing about it? Not by we, I basically mean the global S&T community to meet the challenges, to overcome those challenges. So before I dive into it, let me give a slide on my organization that will set a context to what I'll be talking about. So I'm part of Army's corporate research lab, Army Research Lab. So in some sense, it's Army's NASA, focused on basic applied research, or I guess an Indian counterexample would be some DRDO lab. So our focus is on operationalizing science for transformational overmatch. And let's dissect the sentence. So idea here is that you want to transform the basic science into some actionable products, knowledge that could provide overmatch to the Army. So there are three components to this mission. We want to create knowledge products for warfighting concept, meaning the way Army could be operating in future, we want to provide the foundational knowledge for that. Then there is foundational research, basically thinking on the long-term disruptive, creating new materials, creating new UAVs, creating new understanding science that could translate to some capabilities in the future. And the third one, which is I think probably most important from current, well, equally important from this current meeting, is we are also Army's face to universities, not just within the US, but also across the world. And ARL has international technology centers, which have their role is to identify interesting research going on in different areas and finding ways for us to connect with them. And I think Dr. Harish, he did visit IIT Kanpur a couple of years ago, and he is the POC for sort of finding or making those connections. And this is the same program through which we have continued to maintain our connections with Professor Bharat, who just spoke previously on making use of his expertise towards expanding the science. So we are, I guess, geographically located over different places, and including this extended network of researchers across the world. So now let's get into the UAV itself. So from military point of view, UAVs are disrupting the nature of warfare. So here is a headline from Washington Post, not more than a year ago. It's from November last year. So it's an article on recent war between Azerbaijan and Armenia. And the key takeaway from that episode, that war, is that UAVs are going to fundamentally change the way wars are fought. So Azerbaijan, with help of Turkey and Israel's expertise on different drones, they basically annihilated Armenia in a matter of days. And if you do Google search, you'll find a lot more information about what happened there. But these sentences over here are basically taken verbatim from that Washington Post article. So drones were the key, provided significant ISR. ISR stands for intelligence, surveillance, recon, basically keeping an eye in the air to view what enemy is doing. They provided long-range strike capabilities, ability to shoot far, kill targets integrated with fires from manned aircraft. Basically, these drones could provide an eye, and then this manned aircraft could aim at the target. And then finally, the last bullet basically emphasized some of those drones were kamikaze drones. I mean, they were just effectively, they become a smart munition. You plan them, you target them, you program them, and they are going to take out the target. So based on what happened in this war, and in general, what else is going on, one could say, oh, this is my opinion on what's happening with the trends in the UAV. So UAV or US, unmanned air systems, are becoming part of heterogeneous teams. So they are different components working together, and they achieve towards some common goal. The boundary between US and munition is blurring. You have RPGs, which you fire and you kind of forget. But if you have a US that kind of become munition, then you have this ability to program it. It will basically hunt you down. You can run, but you probably will not be able to hide. Then the third bullet is about the importance of runway independence. And that, I guess, emphasizes why we need VTOL, vertical takeoff and landing. And that basically minimizes the operational logistics that you would need to operate these. And then obviously you need these UAVs across the size and scales to work. So here are the slide shows some of the current UAV efforts in US Army. So starting from the top, so this is a set of group 3. The definition of group 3 is shown in the bottom bar. It's basically classification based on the total weight of these systems. So there is work going on designing this group 3 VTOL US for these 3 attributes that are listed here. Then on right side is UAV for air launch effects. Idea here is to launching a UAV from a flying aircraft and to do things that you want it to do. And some of you may have read recent news article about US-India signing agreement on developing a similar UAV, which is slightly different, but overall kind of in the same area. Then on that bottom right is we have these so-called JTARs, or drones for autonomous resupply. So you want to carry munition, food, water, medical supplies for soldiers at the front lines. And then on the left bottom is sort of this small group 1 US, less than 10 kg total weight. And in there are a couple of different designs, and again, providing organic, meaning something that soldier could keep with them and provide organic capability at different levels of military hierarchy. So this is the scenario in DoD, in military. And as there is an equivalent action going on in civilian application where UAVs are being used for so many different applications. So the key takeaway from this is leads to what do we want out of these UAVs. So this is the slide that sends this message, that information. So we want performance. We want these UAVs to go far. They want them to go fast and carry as much as payload as we want. And some of these do become sort of conflicting, and we'll see that later on, but that is one set of attributes that we want out of the UAVs. The second is we want these UAVs to do the work without making too much noise about it. I mean, that's a good thing for everybody. If you want to do the work, but don't make so much noise about it. Same for UAVs. We want them to operate quietly, that ensure their survivability. And we also want them to be damage adaptable, meaning if something fails, we want them to continue doing their work. And finally, we want them to be agile. And this becomes important if you want to navigate to the forest, if you want to navigate close to Earth, and you want to operate in sort of all weather. So soldiers don't have freedom to take time off when it's raining outside. So in general, if you are interested in one of these attributes, it's relatively easy. If you want both in same design, then things get a little hard. And if you want all 3 of them together, then that's where the real challenge comes. So the goal for us, I guess, as a scientific community, is to understand what is the science, what is the physics that allows us to achieve what we want. And obviously, we want all this at low cost, low maintenance, and high reliability. So now looking at current state of art, or what and versus what is possible. So it's on left, the quadcopters are generally the current state of art at different sizes, at least on the smaller scale. And on the left side is listed some of the limitations that we have with this. Now, I want to show you this clip on basically the possibilities. It's a 1-minute video clip that will show you a hawk going on a sort of attack mission. And I want you to identify or look for key attributes that we think are still, we have a long way to go in sense of creating mechanical systems. So let's watch and watch for those keywords.
He has explosive acceleration. Long legs fire him out of the blocks. Hit attack speed in under 2 seconds. Low profile, hugging the ground, and saves valuable energy. It's hundredths of a second to avoid a collision. Short wings are pulled in to pass through the tiniest gaps. A long tail does the steering, constantly making fine adjustments. To turn sharply, he slams on the brakes by fanning it out, stay hidden until the very last moment. It's all over in seconds.
All right, so so here are a couple of words that were used in this clip, and one could say, I think, with relative confidence that there's we have lot more to do. There's a lot for scientists to work on, and the key takeaway is that then so it's going to require sort of work in design, mechanics, material, artificial intelligence to enable those next generation of UAVs. So now the question is, why is it so difficult to get it all? And so before we go into that, let's have a quiz time. So this is, I guess, my homage to Professor Kamli and Professor Tapan Sen Gupta, and I think most of others have probably retired by now. So I want you to identify these 6 helicopters here, shown here. So these helicopters designed for different applications, and see if you can, how many of you can get them all. If it was a live presentation, I would have asked you to raise your hand and identify if you can get all 6. So the answer is here. So I hope some of you could get more, all, or at least the ones in the last last column. But the key intention of this picture was not really a quiz. It was for you to see the diversity of designs for helicopters, how designs varies from one to other. And so you could see that they are using 1 or 2 large rotors, but other than that, they are very different. And so question comes, why? And so this is the situation for large military helicopters. So they range from several thousand pounds or kgs to up to 50,000 pounds. So this V-22 is order of 50,000 pounds. So this is the situation at large scale. Now, if you look at in this emerging new VTOL concepts, then things are even more messy, or at least more diverse. So these are some of the concepts that have been developed or designed, and some of them have flown as well in last few years. And the ones I want to highlight are the 2 here. EHang, it has already started sort of commercial service in China. And then below that is Joby from a US-based company who should be starting commercial service relatively soon. And I also want to highlight this UAV concept. We saw that in previous presentation. Professor Abhishek has been working on it. Again, as he mentioned earlier, that all of these have their lineage to University of Maryland. And in fact, the concept you see on the right, the Bell, is also same configuration, and also because of the same reasons. They also got, they work with University of Maryland. So now, why are they so different? So both these concepts as well as the design shown on the previous slide. So the answer is basically this. There's an inherent contradiction between design elements for vertical and translational flight. And that really summarizes the challenge for VTOL community. And if you are not careful, then you effectively create a proverbial dhobi ka kutta, whether it's neither good for ghar nor good for ghat. So, so this understanding is what we need to design something which can be good in both those flight modes. So let's start diving a little deeper into why this problem is so hard. So this is one chart which sort of captures the essence of VTOL. So here is a plot that shows on y-axis hover efficiency and on y-axis disk loading. Hover efficiency is a sort of measure of how good you are, how efficient you are in lifting a weight. So basically higher the number means for a given horsepower, you can carry more payload, you can lift more weight. And so that means your rotors have to be larger size, so that over the whole weight is distributed over big size. So one example of how that comes into play is this human-powered helicopter that was designed at University of Maryland. So this is single person cycling, and he could lift off his weight and sustain himself for a couple of seconds. But the reason, what it took to create the design based on this design was somewhere here. You had to be really huge, order of it's in the stadium, indoor stadium, and that reduced the disk loading and improved hover efficiency. Now, on the other extreme is something like JSF. So in principle, it can also do vertical takeoff, but because it's designed for high speed, it has relatively small rotor, a small fan, and that makes it disk loading very high and brings it really down on hover efficiency. So you can do VTOL, but pretty soon you need refueling because it's so inefficient. So that is the fundamental conflict. Now, where do you want to be? And that is driven mostly by what you want to design for. But this explains the challenges of creating a good VTOL design. Now, there's something more. What makes it even harder? So if you look at fixed wing configurations, where we go from 1 pound to 1 million pound, 500,000 kg, the general shape relatively looks unchanged. You have fuselage, you have wings, you have tail, and you have your aircraft. But things got a little different on VTOL side. So on a smaller size, we have these quadcopters. On large size, we have these, there's a big diversity in there itself, but generally you have these large single or two rotor configurations. And in the middle, you have basically big Wild West or kuch bhi. So as it appears as if you just take some rotors, take some wing, put them together, and you have something. And part of that is because we are still understanding what it takes to create an efficient design. And part of it is a lot of new technologies are coming along, which have different impact. And I guess this picture on the in the middle on the right may seem pretty weird, but this is actually a explained program that DARPA worked on, and they did fly a scale model, 300-pound aircraft. So scale makes a huge difference. And then to add to that, so on large scale of VTOL, we have sort of 80 years. So when the first helicopter flew in 1940s, we have a good accumulated knowledge from that time. But on the left side is something which is evolving over last 20 years. So a lot of technologies are coming along, battery technology, the microelectronics processing, and so on. So they're sort of disrupting the design space and leading to all the designs which look so different than traditional helicopter design. So that leads to understanding some more on what difference this scale makes. So before that, so here is a slide that shows sort of what VTOL community as that we can group these different sort of configurations or different concepts in sort of these three categories. So there is this edgewise rotor, typical quadcopter or multi-rotors and so on. They have simpler design. You have rotors that takes off vertically, and then you sort of tilt them and move forward. So simpler design, but that simplicity comes at the cost of inefficiency. Rotors in general they don't like to move edgewise. So one way to overcome that is you have rotors for so the VTOL part, and you have a separate propeller for the cruise part. Okay, so that takes care of inefficiencies, but then that comes at the cost of now you're effectively carrying a dead weight in each flight mode. Okay, so now you can overcome even that limitation by having this sort of tilt-X kind of configuration where you have the same rotor, but you align them according to the flight direction. So that achieves efficiency, but then it comes at the cost of mechanical complexity and the flight control and so on. So, and then obviously there are some configurations which are mix of the two, tail sitter being one example of that. So the key takeaway here is that UAV design space is multi-objective, multidisciplinary constraint. You have and you have to work around that limit to create the design that you want. So now to understand some little more on scalability effect, let's start with this. So there is this square cube scaling laws. So the basic idea is that if you have a object of length L and you double the length, so you go from here to here, your area change like length is squared. So area would become 4 times and volume would become 8 times. So what that means is that if you are looking at 1 pound or 1 kg UAV versus 1000 kg helicopter or UAV, your weight is increasing by a factor of 1000. So your length would change by order of 10. And that has huge implications. It has effect on aerodynamics. It has effect on structural dynamics. It has effect on acoustics. And that comes through these parameters listed here. But let's understand a little bit. So for aerodynamics, Bernoulli's principle is the basic law that we could use to explain how the lift is generated. So basic idea is that if you have a shape, your air flows and higher speed on upper surface leads to lower pressure. And then that leads to the forces. And that force that could be computed by this equation shown here. But things get a little complicated, and primarily because this is really valid for when ideal flow or the lack of the viscosity makes things different. An example is here on the right side. You have 2 aerofoils, same shape, same design, same orientation, and look at the flow behavior. So on the lower one, flow is following the surface. On the upper one, flow sort of separates. And that leads to difference in forces, and that leads to a lot of other parameters. And by the way, this is the same concept that describes the swing of cricket ball. The bowlers try to keep one side smooth, one side rough, so that maybe flow separates on one side, and that creates a differential force and allows ball to swing. And there's something more to it. This phenomena of separation is also scale dependent. That comes through Reynolds number, which is basically describe the ratio of inertial forces to viscous forces. And if you that goes into just to give an example from golf. The reason golf balls have dimples is the size is small, flow is laminar. You want to force it to turbulent flow. And I think we heard some of that in Professor Datta's talk yesterday, how turbulence is helping on Mars. So basically, this laminar versus turbulence is a big deal. And especially in this lower to mid class of UAVs, they operate in Reynolds number where the transition from laminar to turbulence play a big role. And we need to be aware of that and its consequences. So as the scale changes, you have, as I just mentioned, Reynolds number changes big time, and that has a lot of impact. And the picture on the bottom basically shows key differences between airflows for traditional rotorcraft, which have one single rotor, versus sort of these multi-rotors where each rotor is creating its own aerodynamic flow field. They are interacting with each other, and they are leading to those interactions, which can be positive, negative. It can create a lot of noise and a lot of other unintended, undesired consequences. So second part is scalability of structures. So the key idea here is that rotor blades are effectively beam elements. So they're held fixed on one side, and if you move them, they'll vibrate at certain natural frequency. And So we want these blades or any structural elements on flying aircraft to be as light as possible. But that comes at the introduces a stiffness, or that sacrifices stiffness. And so obviously, so basically these systems are elastic. So they'll have certain frequencies, and on these VTOL or any rotary wing aircraft, that leads to this strong fluid structure coupling, and one has to be aware of that. And because this frequency will change with size, just because the length is changing, because inertia is changing, then how that elasticity interacts with design would change with your scale of your configuration. So so in extreme cases, I just want to show you one example of what happens when things can go bad. And I understand that we do have Dr. Datta here, who is a world-renowned authority in this world flutter field. So so idea here is that how a structure and fluid can couple together and can lead to potentially disastrous consequences. And understanding that effect is sort of necessary if you want to create the so-called Formula One solutions for UAVs. Now, the third big area is so the acoustics scalability. So noise generation in general is a consequence of unsteady airflow and blade motion. As blades are rotating, they'll create noise through these three different mechanisms. The next speaker, Dr. Greenwood, is going to be talking a lot more about it, so I don't need to go too much details. But the key idea here is that frequency and magnitude are the key characteristics, and both scale with size. So if your rotor is spinning at high speed, which will happen for if your size is small, then your frequency is going to change. Frequency is going to increase, and that will have effect on how the sound propagates and how the human perceive that frequency. And similarly, as the Reynolds number change, it has effect on the generation mechanism. There are few mechanisms for noise generation which are dominant for large rotorcraft. The thickness, loading, noise being the two dominant ones. And on the smaller size, the third one becomes more important. So again, so both from aerodynamics, from structures, from acoustics, just want to reemphasize this point again. I think it was made yesterday also by Anubhav, that the physics, the science of rotorcraft in this class is very different from large helicopters, just like designing for Mars is very different from large helicopters. So sometimes you may have to almost unlearn what you know about traditional rotorcraft. And that is the challenge for designing a UAV. The design space is huge, new physics is important, and you need to basically be aware of that. So UAV is a lot more than just platform. And so this slide captured some of those additional considerations that need to be understood. And we need to determine what is the optimum choice depending on the scale. So for example, for energy source, we have different options. We have battery, we have fuel cell, we have fossil fuel. So quadcopters will take battery. You will be very difficult to create very small engine, and large helicopters like Dhruva or Cheetah would rely on sort of IC engines. But when you're designing somewhere in between, what do you go? Do you scale down from top or scale up from bottom? So that is the challenge. How do you? Each technology would have its own positives, negative. So determining that based on the science, based on engineering, is a challenge. Next is propulsion architecture. Same issue here. You could go with electric motors. You could go with traditional mechanical transmission coupled to IC engines, or you could go hybrid. So understanding the scale, at what scale, what makes sense. Then you have material manufacturing. 3D printing is advancing rapidly. But then at the same time, there is still some ways to go in terms of determining the strength that comes out of those products. So what is the right place for 3D printing? Then finally, flight control. Again, UAVs generally tends to be over-actuated systems, meaning you have more actuators than the control variables, meaning you could achieve the same flight state by moving different parts. If you have 10, 15 rotors on a configuration, then question is which one do you want to move? Which one do you want to change? So that leads to very interesting flight control and guidance challenges. And then obviously there's a big one on manned versus unmanned. When you are flying a manned rotorcraft, you have to worry about human G limits, but unmanned, you can take more liberties and so on. So these are some of the issues. So now the last section is what are we doing about it? Challenges are fairly clear, fairly broad. And before I go into what we are doing about it, let me just talk about what sort of at least my specific group's expertise or capabilities. So I divide it into 3 groups. So one is this access or the state-of-art modeling simulation tools. So that is our primary role. How do you design? How do you understand through computer simulations? And these are 2 products listed on the left side, which have as a huge DoD effort with inputs of I would say tens, and I may have got close to hundreds by now, engineer scientists. And they have created the state-of-art simulation capability that allows us to get into the sort of high fidelity simulations. Then in my group, we have huge experience in VTOL research experience. These are some of the pictures that we have the different rotor concepts, different configurations, understanding different phenomena that of the basic in-house work. And then finally, DoD has almost unlimited supercomputing resources, which are becoming a critical element of advancing the science that is needed. So with these resources, with this expertise in mind, we have established this so-called, we call it Extreme UAS, with a goal to advance UAV performance, agility, and survivability attributes. So what this, we have seen this picture before. Idea is to having this capability that allows us to achieve all these attributes. And that requires technical capability as shown on the left, and operational which will lead to operational capabilities as shown on the right. And this on the bottom, I show the list, basically the core domain of this research. Has a set of basic and applied research in the areas of aeromechanics, aeroacoustics, and flight control, and operationalize into knowledge products. I'll come to that in a slide or so. So just going into a little more details of what we are doing under each, the key domains of this research program. Now, knowledge products. So knowledge product is basically an idea of how do you, the science that you do, the goal is to publish papers and share knowledge, but also to create some tangible products that could help DoD or community in general to design better products. So Professor Bharat previously spoke about Hydra. So we have been very fortunate to have long-term interactions with him while he was at Maryland and now at IIT Chennai. And this is a product that, and we also have some of our in-house SMEs working jointly with Bharat on creating this capability. So idea, and I think you got to hear his presentation on Hydra. So basic idea is how do you take this design tool to next generation that overcomes some of the limitations of current approach and that deals with the challenges unique to sort of this UAV design space. Now, the second knowledge product that we have in our group is, we call it Stadium. So it's effectively a flight simulation environment where we are coupling a high-end graphics environment with a physics-based model. So idea is that before you fly a UAV outside, you do that in safety at a relatively lower cost of your virtual environment. So challenge here is you want to get the physics of these UAVs. Dr. Kothari showed about that, or even Professor Abhishek, the work they have been doing on quad biplane tail setter. So we have that quad biplane tail setter model in the Stadium environment. So our hope is that what we see in open flight is what you would have see here. So this slide talks about some of the active work going on in my group right now. So there is this broadband noise predictive models. So key idea here is that, as I said earlier, because of scale, there are some unique challenges to noise generation for the smaller rotors, and broadband is basically category of that noise. And I'm pretty sure Eric is going to talk about that in next talk. Then there is this rotor concepts. How do you create these rotors to generate the forces that these VTOL UAVs would need? And again, design space is very different. We want to understand what else is there. Vehicle state aware autonomous flight. So vehicle autonomy, future is going to be autonomous UAS doing things by themselves. Now that decision making for those UAVs will become easy if they are aware of how much energy they have, how much energy they're going to consume, and how much noise they're generating. So this is an area where we want to bring in that awareness into developing autonomous algorithms. And the left side is all aerodynamics. I mentioned about it. Aerodynamics is effectively the key for any flying vehicle. So understanding all that. So now, in addition to in-house work, and as I showed in the first slide, one of our role is also to be face of Army's face to universities. We also want to encourage or develop collaborations with global experts. And towards that goal, we have this so-called Open Campus Initiative, which allows us to collaborate with many partners interested with us, universities, industry, within US, outside US, to focus on challenges which are sort of relevant to us. So interaction with IIT Chennai and Bharat is in a way part of this initiative. And this allows us to, has all the benefits as shown here, not just to us, but also to our partners as well. Idea is to, I mean, as they say, research is a team effort. And idea is to develop these teams and make advances together. So one of enablers for that collaboration is something we call common research configuration. It is based on this quad biplane tailsetter, again, lineage going back to University of Maryland. So we worked on, been working with for years with Maryland. And so idea here is same configuration, built, tested, flown at different scales. And that allows us to understand what, first of all, it provides us a benchmark for different technologies. It allows us to understand what role scale plays in different subsystem technologies. And it allows us to be better at designing these UAVs. So the goal here is not really to design or to create a good or better UAV, but becoming a better at designing these UAVs. And with the advantages, benefits as shown on the right side: foundation knowledge, design capabilities, and helping in enabling technologies. So, so I want to end with a slide. So right now, if we look at what's going on in aviation industry, aviation world, we are at a new era. So to support this contention, let's look at this. In 1903, Wright flights flew the first aircraft with characteristics as shown here. Then in 1940s came Sikorsky and flew the first VTOL or first helicopter with details as shown here. And now in last 10, 15, 20 years, there's a new class of autonomous vehicles coming along. They have different challenges. They have a lot of opportunities to change society, to change the way we operate. So to end with this message, this is an area that has a lot of it for students, for researchers, for industry. And this is my takeaway sentence. Exciting times, let's go exploring. And that's all I have. Thank you.
Thank you, Dr. Rajneesh. It was a really amazing talk and really excellent perspective about the whole challenge that is there in designing these VTOL aerial vehicles and why it requires so much of effort on part of everybody and to come together to solve this together. We have around 10 odd minutes to discuss better. So audience, anybody has any questions, please you can type it in the chat box, or you can even unmute yourself and speak up. So I have one, Anwar is also there. So yeah, I mean, before I ask my question, I would actually like to comment on one thing, that is, you mentioned Professor Kamble and Professor Sengupta. Yeah. So Professor Sengupta retired just last year, I believe. Yeah.
Oh, he did? Okay, I don't know.
Yeah, he did. He just retired and he moved out from here. And Professor Kamble is actually about to move out very soon. So
yeah.
This current semester is actually his last semester, and will be.
Yeah, he did teach us structural dynamics. So.
Right. Yeah, Professor Sengupta, I mean, yeah, is really nice.
He was my BTech project advisor, so I did.
Oh, he was your advisor. Okay, then
yeah.
You are very tough guy. I mean, from your BTech days itself, you chose him as your advisor.
He was the one who got me hooked on to CFD. So he and Dr. Vijay Gupta. Yeah.
Okay. Yeah. So there is one question actually. There are two questions actually. One is from Dr. Ramesh regarding coaxial tilt rotors are viable options for eVTOL. Your comments on that?
Coaxial tilt rotors.
Tilt rotors, yeah.
So, I mean, as I showed earlier, there's a huge design space, and each configuration, each design choice has certain benefits, certain shortcomings. So it's very difficult to say. Answer cannot be yes or no. Answer is what you want out of that configuration. In some respect, it's going to be a desirable approach to create coaxial tilt rotor. But at the same time, there would be some downside that you need to be aware of. And then it really comes down to which one you want to prioritize.
Right. So there's another question regarding whether Hydra or Stadium are open to users from elsewhere.
Yes. Yes. So, but mostly yes. So, as I said, so my organization, I'm part of Army Research Lab. So our goal is really to advance science, not so much to develop products that end users will use. So in a way, our focus is on underlying science, and we want to use this global community. So if there is someone who wants to work with us or want to use Hydra, or then by all means, please reach out, and we'll find a way to work with you.
There's another question from Dr. Ramesh, again, for whether noise reduction can be achieved by using ducted rotors.
Again, the overarching answer would be the same, that a lot of design choices, a lot of effects. So you can achieve noise reduction with ducted rotor in some sense, but then you have to be well aware of the penalties you are, or the cost, what it will cost you. So just to go into more details, as you put duct on a rotor, it helps you in hover. So that is a classical equations you can try. But the duct is also adding weight. So you have to, at least purely from performance point of view, you are losing something. So now reducing noise at the cost of performance is a very well-known trade-off that we do. So now whether you achieve noise gains by using ducted rotor, adding weight and losing performance, or you reduce noise by maybe even slowing down tip speed, so which also has effect of reducing performance. So that again comes back to your choice, or what else do you want in that design to do. So answer is sort of qualified yes.
Then there is another question on what is the current status of Hydra?
So Hydra is work in progress. So we have been working with the University of Maryland, now IIT Chennai, for over 5-6 years. It has come a long way, and in some sense, it has sort of change paradigm of UAV design, and or at least the approach it's using. But then potential is also huge. So Professor Bharat mentioned how some of the challenges that that are motivating work on Hydra, that you want to reduce reliance on empirical data, which is not available when you are creating a very non-traditional design. You want to bring in better physics into the design, conceptual design stage, so that you have better estimate. Now, if you think forward, what else can be done? So getting this good aero or getting the good weight are the two challenges of any design code. So we can keep on bringing high fidelity, and high fidelity generally means you need more computational resource. But as hardware is improving, there is opportunity there to see how much higher fidelity we can bring in. Then there is altogether a different field, different area of how can artificial intelligence and machine learning can impact your design process. Generally, design has sort of two elements. There's a human creativity element to it that comes from the experience or knowledge of the designer. And then this other element of these tools, the method of calculation. So feasibly, that human creativity can be replaced or at least augmented by the work which is going on in AI and machine learning. So that is huge area of research. Then another big area would be that, as Bharat mentioned, that we have decisions made at conceptual design have downstream effect on later on prelim design, final design, and any change that you make downstream turns out to be more difficult to do. They can be more costly, and they're difficult to achieve. So more and more we can finalize the design at the early stage, so that this iteration of back and forth is minimized, is good. And that would be another goal for Hydra. So there are a lot of things that can be done. And again, if you have some ideas on how things could be done, I'd love to interact with you.
So there is yet another question on coaxial rotors. I think, after Anubhav's presentation, now the coaxial rotors are actually right now very famous. So another question about whether one can put a shroud around a coaxial rotor. Would there be any advantages of doing something like that? Because rotors are spinning in opposite sense and the wakes are going in a different direction. So I guess that's the idea.
Assume again, general question would be qualified yes, but so there are a couple of things you have to look at. So how does the benefit of shroud manifest? It's basically shrouds are preventing the wake contraction, and the lower pressure on the upper the lip abduct are generating negative pressure, which helps in augmenting the thrust that you're generating. So those are the positive things. But then you have to also consider the price you're paying for it. There is the weight I mentioned earlier, and there is also the aerodynamic drag. So faster you are flying, more drag you would have. That will take away from thrust. And the third one, which is I think probably equally or even more important, is the effect on the control. So especially when you have ducted rotors or shrouded rotors flying edgewise, you effectively have a sort of block body which is trying to move through air. And as the air goes over the lip, the flow becomes the symmetry is lost. And that leads to some pitching moment, undesirable pitching moments that can have sort of negative effect. So yes, in hover, you would probably benefit by putting shroud. You are going to lose a lot of that advantage faster you fly. And then there would those additional penalties of weight and drag and so on.
So there's a next question is actually on a possibility of using a hybrid, that is having an onboard generator with a IC engine kind of setup. Whether such a system is being explored for helicopters and especially for tail seaters actually.
It is being explored. So I mean the hybrid propulsion, IC engine driving, right, generator and electric. Right. Yeah, this is a huge area of research in VTOL field. And again, so the key theme for my talk was, I mean, if I want you to take one takeaway from the presentation is the effect of scale. So same for hybrid propulsion, it comes down to scale. You have to determine where it would make sense. It's not going to make sense at 20, 50 pound heavy rotorcraft. It's probably not going to make impact at 10,000 pound rotorcraft. And in fact, it did not, I mean, the DARPA VTOL explain, it did try that, and it was probably ahead of its time. So because of the scale and size, it did not work. And primarily because if you take electric motors, they have certain scalability. If you try to make them really huge, then the weight really starts shooting up fairly rapidly. So then finding the sweet spot of where the technology works, which in my opinion is order of few hundred pounds, so maybe low thousands, that is where hybrid propulsion has a huge role to play. And that is something that's a huge area of research. Again, Professor Datta is in the audience, and he has worked quite a bit in that space too. He's everywhere in VTOL.
So the next question is, somebody is mentioning that he has seen some prototype in which swash plateless rotor is used. That is a good option to control the motion of helicopter. So that's more like a comment, I would say, than question. There is a long question here. VTOL UAVs and fixed-wing UAVs, which one you think has advantage over the other, and which one is easier to manufacture? I think it's actually from one of our second-year UG students, because he has his roll number in front of his. I can make out. So,
Okay.
So he says in your attack formation, which one will be more lethal? I mean, having a swarm of really small conventional drones, or having two or three large UAVs like, say, General Atomics. MQ-1C and so on. Okay, so that is his long question.
Right. So good question. That's a fundamental, I guess, decisions, or the issue comes up all the time, VTOL versus fixed wing. So again, answer is, what do you want this UAV to do? So VTOL has the benefit of taking away need for infrastructure. I mean, US Army has a well, they have, I think all armies probably have UAVs, fixed wing UAVs that require some launching mechanism, catapult launch, or and capturing through some mechanism. So if you don't have VTOL, you need this huge logistics cost. So you want VTOL from that perspective. Now, but VTOL costs you in terms of endurance. I mean, you just cannot beat fixed wings in terms of endurance, in terms of range. So then again, it comes down to what is desirable. I mean, if for things like ISR, the intelligence collection, eye in the sky kind of mission, you probably want a UAV that can be in the air for a long time. So it has to have wings. I mean, this quadcopters would not be able to last for more than a couple of hours at best. So yeah, the answer is, yeah, both have their own sweet spots, and that decides what you want.
I think we can take one last question, that is on the role of smart material. So is the use of smart material being explored in VTOL UAV designs versus regular conventional material?
Yes, I mean, smart materials are huge enabler to achieve next generation performance. I mean, especially if you want to create the so-called bio-inspired designs, where your configuration, your concept can go from one form to other, and that you would need, because as I showed earlier, that the design elements for vertical and translational flights are quite different. So a smart design would be something that is sized, or that looks optimum for hover mode, and then somehow transform into a different shape that is ideal for cruise flight. So smart material are ways to do that. So smart material, active material is a huge area of research, but then fundamentally question you have to answer is, does the complexity by its weight? And if you are using a certain UAV in operational space, you want to have good reliability as well. You want to have low maintenance. You have to have low cost. So UAV being a system, all these factors come into play, and that really decide. Technical solution alone is not enough, but then we have to, since it's an enabler, we have to research in that and see how far we can take it, and that's the challenge for I guess the young students, research community coming along. How do you make this far reaching technologies feasible for UAVs?
So I think the time is up for us. So thank you so much, Dr. Rajneesh, to give such a enriching talk and also answer so many questions. So we have our next speaker ready. So let me just quickly share my screen.
Okay. Thank you, Abhishek, and thank you, everybody, for spending a Friday evening with us.
So the next talk is by Dr. Eric Greenwood. So Dr. Greenwood is an assistant professor of aerospace engineering at Penn State. And prior to joining as faculty, he was a researcher in the Aeroacoustics branch of the NASA Langley Research Center. And Dr. Greenwood conducts theoretical and experimental research to better understand the aerodynamics and acoustics of rotor and propeller-driven aircraft. This includes the development of rotorcraft noise prediction methods, such as the fundamental rotorcraft acoustics modeling from experiments called frame technique, and the design and execution numerous laboratory and flight experiments. He has designed and executed numerous laboratory and flight experiments. He has received numerous awards, including 2020 Alfred Gesso Award and 2018 François Xavier Bourgeois Award from the Vertical Flight Society, and 2016 NASA Early Career Achievement Medal. So with this brief introduction, I will request Dr. Greenwood to share his slides and start the wonderful talk.
All right, wonderful. Thank you so much. Excited to have the opportunity to speak with you and tell you a little bit about this particular vision I have for how we might be able to enable low noise, to say ultra low noise, vertical lift operations in the near future. So let me get my charts. There we go. Oh, there we go. So I just want to start with this. So this is kind of NASA's vision chart for what urban air or advanced air mobility might look like. So the near future of our airspace. And right, we have lots of different vehicles that are operating in and around our community. Certainly the kinds of aircraft that we're used to seeing before, but the exciting new thing are, all of these new vertical lift vehicles that are taking people and things from point to point, right where those people and things need to be, right? And that includes everything from, larger air taxis and logistics vehicles to smaller UAS, right? That might just be delivering a package in a timely sort of way. So I don't know about you, but in general, like this is a future that I want to live in. And, we want to see this come into place. And certainly there's a lot of energy and enthusiasm behind this idea these days. So this chart is a little older. It's one that I got from Airbus A-Cubed. So it doesn't include the effects of the current global pandemic. So maybe shift these curves over to the right a little bit. But it's a plot of basically aircraft operations in terms of number of flights per year as a function of time that's predicted based on market projections. And I'll note to you on the left-hand side for our y-axis, number of flights, that's in a logarithmic scale, right? So every line is another order of magnitude of additional flight operations. So that yellow line there, that represents the present day and then future predicted growth of commercial aviation operations today, so mostly airliners. And if we look, the first little line, that blue line that starts to come up, right, and it is coming up now, is commercial operations for package delivery using small UAS, right? And we can see there, the predictions, kind of the market demand estimates here. We're talking about going from hundreds of millions of flights per year to billions almost flights per year, right? An order of magnitude increase. And that change happens quite rapidly, right? Over just a few years, the prediction. And then we'll see. When we look at urban air mobility, so here we're talking about these larger vehicles that might be carrying people, they might be carrying larger amounts of cargo, say from one warehouse to another. Here, the projections show over almost a similar span of time, maybe a little bit slower, an increase in number of flight movements from below what commercial aviation has up to now tens of billions. Right, so just 2 orders of magnitude more operations than we have, say, for commercial airliners today. Right, and of course, as we have a rapid change in the number of vehicles that are operating, we expect there'll also be a pretty quick change in noise, and people don't like change in their communities and environments that happens quickly. And then the other thing to think about is that these operations are a bit different than regular commercial aviation in that, in order for them to do good, for them to do the exciting new things that we want them to do, they have to operate in our community, right? That's why vertical lift is so important, so they can take off and land in places where we don't have big infrastructure for them. And, so they're going to be close to people that can hear them throughout the entire flight. And if we look, the closest thing we have here today are helicopters. And, if I look at the flight volume of helicopters today, they're probably less than one, or an order of magnitude less than commercial aircraft operations. And most of those helicopter operations today don't happen in populated places, right? They're utility operations and things like that, agricultural operations. So there's a small portion of helicopter operations that occur relative to commercial aviation today. And yet, right, if you follow the news, right, people are not very happy with the helicopter operations that we do have today. And this is a global problem. Public acceptance of these operations is clearly decreasing, and there are not very many of them. If I talk to my colleagues, say at FAA or other places, they will say that over half the noise complaints they receive are due to rotorcraft operations today, right? And here you're talking about just a handful of aircraft. And usually, right, that's that community annoyance, public acceptance of these vehicles is linked to noise. And we can argue a little bit about whether, it's really the noise itself that makes people upset about these vehicles, or if it's just a trigger, right, makes you notice that there's a helicopter operating nearby and there's some other reason that you're not happy about that. But ultimately, the real fact is that this is really hurting the helicopter industry because operations are being limited due to noise, right? In lots of places, like in New York City, they have restricted the amount of operations that can happen by half, right? And that's money out of the pockets of operators. In France, I mean, they've so really heavily restricted operations over metropolitan areas. So anywhere where people live, it's basically public service operations only. So it's having a real effect. And I bring this up as an example because if we go back to our chart here, now we're talking about 3-4 orders of magnitude more vertical lift operations in and around the community. So these vehicles can't just be quieter; they have to be dramatically quieter in order for people to accept them, right? So let's start then by thinking about where does rotor noise or the noise of rotorcraft come from, right? And we'll go into a little bit of the technical details to kind of get you familiarized here. So, and Rajneesh had talked about this a bit during his talk, right? And we can principally say that the noise that comes from rotors is going to come from 2 major sources, right? And this noise is generated aerodynamically. And one mechanism here is what we call thickness noise. And I've shown an equation here, and I promise there are not a lot of equations in this talk, but this is the Fox-Swain-Hawkins equation. And the term here that's shown in red, let me see if I can get my laser pointer out. There we go, is the term for thickness noise. And thickness noise is caused by the displacement of air as the rotor blades pass through them. And then the other source of noise is what we call loading noise. And loading noise is basically caused by, our rotor blades have to generate thrust, right? So they've got aerodynamic forces that are applied to them that generates their thrust and drag. And of course, from Newton's laws, those forces that are pushed on the rotor, well, the rotor has to apply those forces back to the fluid, the air. And that application of force to the air, right, also causes an acoustic effect out in the far field. So a few things to notice here, right, in front of both of these integrals, we have some kind of derivative. So we have time derivative on the loading noise. We have a space derivative. Because this is a solution to the wave equation, there's an equivalence between space and time. So that means that whatever is happening inside of this integral needs to change over time in order to generate noise. And what's unique about rotorcraft is that, even if the source mechanism itself is steady, so say like the displacement of air around a rotor blade when the rotor is hovering, right? That's going to be a steady kind of term. It's not going to change as the rotor goes around the rotor disc. That still results in noise. And that's because of what we call convective amplification. So if I look at the denominator of both of these equations, right, I've got a term that looks like 1 over 1 minus the Mach number. And this R means in the radiation direction. So as the blade comes toward me, right, this Mach number in the radiation direction, say for a helicopter, is going to approach 1. So this denominator is going to get small, and this term is going to get really big in general, right? And then as the blade comes away from me, the opposite happens, and the term grows lower, right? So this convective amplification drives noise, and it means that even steady sources can generate noise once I start rotating them, right? And and as Rajneesh had mentioned, right, smaller rotors are going to be generally governed by the same sorts of mechanisms, but because they're smaller, everything's going to happen at a higher frequency, right? The blade passing, the rate at which the blade passes, the rate at which this convective amplification term is driven, that's going to increase. And then we'll talk a little more about the details of some of these other mechanisms as we go along. So I want to start out by talking about one mechanism we've studied a lot for helicopters, and it's an example for things that can happen on other rotorcraft, and that's what we call blade vortex interaction. And blade vortex interaction basically happens when the rotor blades interact with wake that's been shed by a previous, blade, or a blade that was basically shed at kind of the leading edge of the rotor disc up here, right? So as that those vortices are trailed, I should say, from the rotor blades, right? They form this wake, and then the blades will come back past them. And as that happens, right, the vortex induces a velocity onto that blade. And as the blade passes, there's a rapid change in angle of attack, right? And the magnitude of those loads might not be that big. But if you go back to our Fox-Williams-Hawkins equation, I have this derivative, effectively a time derivative. So when I take the time derivative of a rapid fluctuation in loads, I get an impulse, right? And that impulse has a lot of high frequency content, and it tends to be very annoying, right? So that's the kind of stuff, that's that wop, 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 wop sound that you kind of associate with helicopters. That mostly comes from blade vortex interaction. What you can easily imagine here is, right, because this depends so much on the relative position of the rotor wake and the rotor blades, right, it's extremely sensitive to changes in the operating condition. So for example, if I have this helicopter in a shallow descent, right, the wake's going to tend to convect below the rotor, and I might not generate that much BVI. As I steepen up my descent, right, the wake in the rear area of the rotor disc is going to get closer to the blades. I'll start to produce more noise. And I may reach a peak at really intense blade vortex interaction. And as I go even steeper, maybe I can get the rotor wake up above the rotor, and the BVI starts to go away again. And this same kind of stuff can happen during maneuvering flight, right? Accelerations, decelerations, all sorts of other things that I can change. And that makes the noise in general very sensitive to the details of the operating condition, right? And the aerodynamics around this rotor. And unfortunately, that makes it, as engineers, right, makes it really difficult for us to compute this stuff and make a prediction a priori, because it's extremely difficult, especially as the wake, goes through more and more time for us to predict exactly where it's going to be. So that's the bad news. But the good news is that this, because of these physical mechanisms are so sensitive to the operating condition we have, it gives us an opportunity in order to fly these vehicles more quietly, right? And so here is an idea of some existing noise abatement guidance. This plot here on the right comes from the Helicopter Association International's Fly Neighborly Guide. I'm on the Fly Neighborly Committee. So this is training material that we put together to try to synthesize some research that have been conducted over the years to tell helicopter operators how they can fly their machines more quietly. And this plot here on the right is what we sometimes call the fried egg plot, because you can kind of imagine it looks like an egg that I cracked on a pan. And it shows me basically the region where the helicopter is expected to be loud as a function of the airspeed of the vehicle, and then the rate of sink or rate of climb, right? So we can see here, I get intense blade vortex interaction at a particular sink rate and airspeed combination. And then as I go above or below that sink rate or airspeed combination for this particular helicopter, right, I can hopefully avoid VTI. So maybe the pilot can use this information, right, in order to come up with and devise some approach path, say to come and land at a vertiport, that's going to take you out of that noise sensitive region, right? Now, the problem here is, these materials, this kind of stuff has been collected largely for steady flight conditions. So back when this plot up here in the upper right corner was generated, they put a microphone in the helicopter and they would fly each of these airspeed and sink rate combinations and measure how loud it was. The other thing is they're for practical reasons, they're all kind of collected at the same set of operating conditions or atmospheric conditions, right? So, you're gonna fly your helicopter wherever you are, say the sea level and 70-degree day Fahrenheit, so say 15 degrees Celsius, and you'll fly different combinations. But what happens as I change those ambient conditions? And certainly we know, if you go and you fly a helicopter up in the mountains or somewhere else, the aerodynamic performance of that vehicle is changing. And given that all the noise is generated by aerodynamic sources, we expect the acoustics to change. So this is what I spent a lot of my time at NASA studying. And, over the 10 years that I was there, we learned quite a lot of things, mostly that this sort of simplified approach is not telling the whole story, right? So where this blade vortex interaction noise can occur is going to change quite a bit depending on what the vehicle's doing and where it's doing it, right? So if I'm at a high altitude, I may shift where blade vortex interaction occurs. If I'm decelerating or accelerating, I'll change where it occurs. If I'm in a turn or I'm doing a maneuver, it's going to change where those things turn. It'll change if I change the weight of the vehicle because I've changed the payload or if that added drag, right? And what that means is, I can't rely on some generic set of operations that are going to be effective for noise abatement everywhere, right? That's sort of what we've learned. So what we need are operations that are really tailored to the specific mission that you're going to perform. And that in and of itself is a bit challenging, right? Because unfortunately, the world for this planning, the world we live in is very dynamic. The weather changes every day, and we've designed as part of Fly Neighborly helicopter operations for places where they had noise issues, only to find out they could rarely be flown because the cloud ceiling was too low, right? So the vehicles could get up to the altitude that they needed to be at, or air traffic changes, and that means the flight routes have to change direction to the vertiport. Likewise, especially for vertical lift aircraft that are trying to do on-demand missions, I might not even really know exactly where I'm going and what I'm trying to do until the moment of that flight, right? So we need approaches that are more flexible so we can really get the most out of these noise abatement operations. So this is the big idea I want to share with you today. Right, which is this idea of acoustically aware aircraft operations, right? So we want to be able to provide, enable these ultra quiet vertical lift aircraft operations, which are going to be timely and specific, and maybe even most importantly, intuitive to the operator, right? So they don't have to spend a lot of bandwidth kind of mentally focusing on noise when there are other things like safety, right, and executing the mission to focus on. And we want to do that by kind of relying on a sense of autonomy, right? Can we have our vehicles have some awareness of the noise that they're putting out, right? So that they can either inform the pilot as to what to do, or if they're an autonomous system, inform that autonomous system as to what to do to minimize noise, right? So we could view this as a subset of the vehicle state aware autonomy Rajneesh talked about in the last lecture. So we need some things to make this happen, right? First, we need to have really, really fast aeroacoustic models, and they should be accurate if they're going to do us any good, right? We want, if we're going to come up with timely operations, right, we need to get answers quickly as to what noise that this vehicle is going to generate. We're going to need then to apply these models in real time, right, in order to provide us some information we have about the acoustic state of the vehicle. right? And then finally, we want to be able to use that acoustic state information in order to generate on the fly some guidance, either for the pilot or for an autonomous system, that's going to minimize the acoustic impact of those operations. And then hopefully, still consider and maintain the performance of the vehicle, its efficiency, right? We don't want to reduce, say, the range we can fly, and then maintain things like passenger comfort, right? If we have people in there, I can't be doing a bunch of aggressive maneuvering. So we'll look at each of these things in turn. So I'll start here with fast and accurate, hopefully, noise models. And like all good engineers, right, when we're tackled with a problem where we have a lot of data and a complex model, the first thing we ought to do is go and apply Buckingham's pi theorem, right, and try to non-dimensionalize this problem. And it's well known, certainly the rotorcraft aerodynamics community, but then this equally applies to acoustics, which we can view as a subset of aerodynamics. That essentially the operating condition of the rotor can be viewed as governed by some set of non-dimensional non-dimensional governing parameters, I'd say, right? And there's lots of different combinations that you can look at. So I tend to use a wake skew ratio, which basically defines the slope at which the wake on average comes off the leading edge of the rotor disc as it trails back toward the rear of the rotor disc. You can also use like a rotor angle attack to tell you simpler information. Thrust coefficient, right, and on the initialization of the thrust, that's of course going to control, say, the strength of the vortices that we have in our wake. And then the hover tip Mach number. The tip Mach number is extremely important for acoustics, right? We saw how it existed in that convective amplification term that drives all of our noise sources. And in combination with the advance ratio, right? Those both tell us how the wake and the inflow through the rotor is going to look, and then also what the blade section Mach numbers are along the entire span, right? So those are the sorts of parameters we want to use to determine what acoustic state we have. And then we're going to introduce here an assumption that we can look up that data, quasi-statically, right, at every instant in time, and then come up with some model of the resulting noise that's associated with that state. And we have a code here that we've developed to do some of this based on some previous work I've done. There's a cute acronym here, NICEOPS. I won't go through the whole acronym. And the idea here is that we can basically use either experimental data or predictions, or ideally some combination of both, right? So we get both something that's grounded in reality, but lets us generalize to other operating conditions. And use that to build up kind of offline, when I have lots of time, a pre-computed database of noise as a function of those non-dimensional operating conditions. So this is just one example where we have flight test data that we took from the A-Star helicopter, and then load that into a machine learning model, in this case, of the noise emissions as a function of operating condition, and have basically, this model gives you the frequency and amplitude of noise as a function of directivity angle for that particular operating condition. And we repeatedly apply that in order to build up a database of essentially acoustic spheres that represent the noise for all these different operating conditions. So it's just one way to do it. And then what we can do is, when we want to make a prediction really quickly, right, we can use just a very simple kind of point mass flight dynamics model to estimate what the rotor state should be at every point along the trajectory, and then associate that with some this aerodynamic state for the rotor. We then pull out the correct acoustic sphere and then orient it with the predicted orientation of the vehicle for that point in time. And we can then use a very simple kind of linear model of acoustic propagation in order to propagate the noise from the surface of that sphere to observers on the ground very, very quickly, right? And it gives us the ability to rapidly analyze different sorts of trajectories and maneuvers. And just some validation data. The data comes from the last flight test I did with NASA, which here's the NASA Mobile Acoustics facility, and we took noise measurements of helicopters on approach. This is an S-76D. On the upper left-hand corner, these are the measured, and the measured locations are shown in these white circles. Sound exposure level, so it's an integrated noise metric over time. So it shows, in a sense, all of the acoustic energy that this vehicle put out throughout that entire approach down to our landing zone, which is kind of just ahead of this contour. And, we had a limited area, of course, where we could place microphones. So we used this tool to predict those noise contours everywhere else. And you can see in the area where we measured, we get pretty good agreement in terms of the noise levels, right? So hopefully gives us a little confidence in that. Another aspect where we can apply this sort of noise modeling is to things like maneuvering flight, right? And in maneuvers, here the vehicle may rapidly change its orientation. It may rapidly change the aerodynamic state of the vehicle. And the combination of those two things mean that if I have a microphone on the ground, I may get a sudden increase in acoustic pressure due to blade vortex interaction and other interactions, right? And that's what we show here, right? So we can get that through maneuvers. They don't even have to be all that aggressive. And again, we can apply this kind of quasi-static technique to predict noise for these sorts of maneuvers very, very quickly. And here just are a couple of other comparisons from a different flight test of a microphone. These are the sound pressure levels as a function of time over the course of a pitch up maneuver on the left and an advancing side roll on the right. And the black are the measured data. The pink line here, that's that quasi-static model. And the blue line is kind of a purely steady state model, like a lot of the kind of modeling that was done before these tools were developed. And what we can see is the pink line does a pretty good job kind of quantifying this increase in noise that's caused by the maneuver relative to the blue line that doesn't show that. The exact details of the shape maybe aren't exactly correct because of the quasi-static assumption, but the magnitudes are correct, right? So we've done a pretty good job capturing this acoustic impact, and the acoustic impact can be quite large. It could be 10 dB. That means I'd be able to hear that noise, the same level of noise at a distance away from the vehicle that's something like 4 times greater, right? So it's quite a lot, a big impact, or you can think of that as 10 times the area, right? So it's a big change. So now we have a fast tool. We'd like to apply that to kind of rapidly predict the impact of different sorts of flight operations on the noise that we generate. And this just gives you an example here of some ground noise contours, again, for a helicopter at instants in time as it does a turn. So when we roll into that turn, we make a bunch of noise due to BVI. So we start to go around the turn, the noise goes down a little bit. As we roll out, we get another burst of noise. And then the same kind of way, I can take a sound exposure level and integrate those all together and come up with one set of numbers that represent that whole turn. And I can do this with this kind of modeling, for 2,500 observers, so a pretty high resolution contour for an 80-second maneuver and about 175 milliseconds of time. So much faster than real time, right? So when I have this fast model, my first intuition might be maybe I ought to wrap an optimizer around it, right? And find out how quietly could I fly. And then so I took a shot at doing that. And this here's some details about the optimization that we've done. It's not a convex function, so you need to use some kind of global optimization approach. But you can work to minimize that average sound exposure level on the ground. And even though the model's fast, this takes tens of thousands of iterations. So we're talking about a few hours. Right. But when I'm done with that, I can see a pretty big reduction in noise, right? 10 dBA on average everywhere, and as much as 20 dB in some locations, particularly toward the outside of the turn, right? So really, really pretty effective compared to kind of what I'd say that it's sort of naive or standard approach into landing from a turn. But the problem again is this takes a long time to compute. It's not timely enough to be useful. So what else can we do to get towards our timely operations? Well, one idea is maybe I should just use the pilot as my optimizer, right? So if I can give the pilot some information, some awareness about the noise that's coming out, maybe I can use that. This is the noise display that I put together since I've been here, but with some folks at NASA that does a real-time prediction of noise from the helicopter. We hooked this up to a flight simulator. You can't see the output here, but here we actually took this to HAI Heli Expo, and we had a bunch of helicopter operators fly the virtual 407 on the simulator, and then they could see a display of the noise that they're putting out. Right. And as you watch this display, you can see that noise footprint can change quite dramatically pretty quickly too. Hopefully give the pilot some idea for their particular operation. What can I do to avoid having this noise footprint overlap where the places on this map where people live, where I'm getting noise complaints? This is actually really popular. We have a lot of people who want to get their hands on this sort of simulator for flight training. So they can practice flying in and out of their home airport, and very fairly, right? none of these helicopter pilots wants to be staring at this display when they're actually trying to fly an operation with people in the helicopter, right? Because they've got lots of other, more important safety critical things to think about at that time, right? So I think we need to do a little better. We can't rely on the pilot to do all the work because pilots got plenty of work to do already. So the next idea here is then, well, can we provide some kind of guidance on the fly? And we can't use that conventional kind of direct trajectory optimization approach because it's much too slow. So we got to be a little more creative here. And the answer comes from, well, maybe if we could cache essentially all of the noise data as a function of operating state, maybe we can cache even more information to help us generate trajectories very quickly. And the idea here is that we could take what we call a combinatoric optimization approach, or like a graph search. And this is done all of the time for non-acoustic type trajectory planning. And basically can say, if I pre-calculated the noise for a bunch of different maneuvers, could I then somehow connect all of those maneuvers together to get from where I am to where I want to be, right? And that ends up becoming a graph search problem. And there's lots of good algorithms for solving graph search problems. So the way we do this, and this is the other equation for the talk, is using what's called an A-star search algorithm. So in this case, we have some heuristic function that we apply to our search algorithm. And we're basically saying the cost we're going to estimate the cost to get from where we are to some other point. So say like from this red X to the red circle, is just going to be that Euclidean distance multiplied essentially by the best case acoustic cost. So if we flew the quietest possible maneuver over that distance, what would be that cost? This gives us a heuristic, kind of like a lower bound for the quietest possible path from A to B is defined by this heuristic, right? It has to be less than the true cost if I actually added up all the segments it took to get there. And that lets me do things where, for instance, if I've already found this gray path, right, and it has a lower cost than the heuristic line for this other node, then I can reject that node. I know there's no possible way that if I walk to any path that passes through this red X is going to get me to the endpoint in the red circle, any lower of an acoustic cost than the path I've already found, right? So I don't have to search over it. It saves a bunch of time. So I'll give you an example here. So this is just kind of a mission planning operation. We're going to take off here and then land somewhere else 40 kilometers away. And this blue square represents some portion of the airspace that's closed off to us, right? And this area that we're going to search over is kind of the size of a moderate sized city. And this represents, like 20 minutes of flight time. And we can come up with an answer for that in about 40 seconds. Right, and there's a 40 seconds between each node, so we could even change our answer between nodes, right? So we come up with our approach. Here, the size of the circle represents how fast we're going, and the color represents the altitude. And the trajectory we've come to go from A to B is basically take off, accelerate, get up to a high altitude, then do your maneuver, right? So you don't make a bunch of noise, and then try to come back down to your approach path. And of course, we can then come back once we've figured out that path and then actually simulate the noise radiation and come up with a noise footprint for the entire path and check our answer. Now, if our airspace changes, because of weather or some obstacles, well, we can do some replanning and come up with another path. And because we've already searched some of these nodes, it's a little bit cheaper, right? It'll take us now 30 seconds to come up with that other path. Now, the cool thing and why I mentioned the A-star algorithm is we have some tools, some tricks we can use to accelerate that, right? So I'm still 30 seconds is good, but it's still not really near real time. That's where we want to be. And this is an idea, this anytime A-star algorithm, where I can essentially overweight this heuristic. So I can say, well, if I'm using the heuristic to reject points that can't possibly be better than the ones I want, maybe I could reject even more points that are not likely to be better by increasing or inflating this heuristic by some value epsilon, right? Now, the problem I have is I'm no longer guaranteed to get the lowest noise path, but at least I can say if I inflate this heuristic value by 10%, well, the cost, the increase in the cost could be no more than 10% as well. That's provable. So we can look at some overweighting here, and this just gives you different factors for epsilon, so 110%, 125%, and 200%. And we can see we get kind of reasonable low noise paths for these each of these cases. And as that inflation happens, right, we save a lot of time. So just a 10% overweighting takes us 10 seconds down from 40 seconds, right? 25%, we're down to 3 seconds. 2%. Or 200%, we're down to 25 seconds, right? So double overweighting gives me 120 times speed up in this calculation. So I can do it as quickly as I want, basically, by inflating that. Now, if I do get some of the details, I see that I get more wiggles, sort of more maneuvers and turns, especially near the endpoints here, as I really, really overweight this solution, right? And that's where some of these other considerations need to come in, right? So in this case, we're modeling the vehicle as a point mass. We don't really have a pilot model, but we can go back over my trajectory, right? And then try to figure out, how difficult would it be for somebody to actually follow this guidance using sort of a simple model of the interloop pilot crossover frequency that comes out of that trajectory. And so here is just a bar chart that we've plotted different bars that sort of show this normalized pilot crossover frequency, the value of which doesn't mean that much. It's really just the relative changes. And of course, we can see it gets harder to fly each of these trajectories in general as that overweighting increases and I add more wiggles. And especially in that yaw direction, because I'm doing lots and lots of heading changes, because I'm kind of confined to the structure of this graph, right? So I can only fly at those nodes, into those nodes, or out of those nodes at certain headings, which really is a rigid constraint. So that's just to give you an idea. We should follow some other things. So here's just a short little clip to show you this dynamic replanning in action. So here we got a helicopter operation. We planned from the city center to some outlying place, and the helicopter right now is at this red star. And we're going to move in 5 seconds this chunk of closed airspace somewhere else, and then let the system respond. And the idea here is, again, I can run in maybe even in parallel different calculations with these inflated heuristics. And as time goes on, we'll start moving now, I can refine my path, right? So here my obstacle is going to jump, and I almost instantly come up with some new path, at least gets me going in the right direction. And after just a few seconds, I can refine that over time as I have that time, and come up with a better, closer to optimal trajectory. So that's all stuff that we can apply right now today, actually, to helicopters, and then hopefully it'll be useful. But the new exciting thing, and the thing that really gets us worried about noise these days, are what the FAA would refer to here as unconventional aircraft, and what a lot of us in the community are talking about is unmanned aerial systems, multi-rotor types that, like Rajneesh was talking about, and urban air mobility vehicles, so more the man carrying and cargo logistics types of things. So when we look at those vehicles in terms of acoustics, what's going to be different? What do we need to account for when we want to try to integrate this stuff into this idea of acoustic awareness? So certainly when we look at all of these different vehicles, first of all, most of them have some form of electric propulsion. And certainly the opinion here has changed as people have realized what's happening, but having electric motors in and of itself doesn't help you with anything acoustically, right? The noise of a helicopter is not primarily coming from the engines, right? So switch to electric motors, they may be quieter, but they're not a big problem. The power plant was a problem in the first place. On the other hand, right, and it's clear that most of the actors in this industry now that are trying to develop vehicles know that noise is going to be a problem, and they prioritize it. And so they are tending to operate at lower tip speeds, right? And that's kind of a first level effect that I can do. And the other thing is that having electrification, right, the real benefit of electrification is that it enables this idea of distributed propulsion, right? So I can now, at relatively low cost to weight, have lots of different rotors and propellers and fans that maybe do some combination of lifting or propulsion. Maybe they do one or the other, right? And when I look over the field and survey it, the big thing is there's a really, really wide variety of configurations, and they're all much more complex. From a configuration standpoint, I have many, many more rotors. I have a lot more potentials for aerodynamic interactions than I had before. So I mentioned tip speed, right? And that's an important thing to look at. So this is a quick little calculation I did using some of our tools here, like the SB WOP, just to predict the kind of variation we would have in noise for a notional eVTOL rotor, so a 3-meter diameter, 0.2 solidity rotor that's kind of loaded up. It's in the ballpark of some of the other rotors out there, like say Joby's, and done a prediction for the noise levels in hover as we change the tip Mach number of the vehicle. This is quite close in, so the noise levels are it's only 15 meters away. What you can see here, right, is at high tip speeds. If I'm running this thing at a tip Mach number of say 0.8, like a helicopter, like the Huey, right, it's very much thickness noise dominated, kind of in the plane of the rotor, but that rapidly decays as the tip speed goes down. Loading noise decays a little more slowly, all right, but it still becomes less and less prominent as the tip speed goes down. And by this kind of loading noise, I really mean steady loading noise, just the loads that are generating thrust, not unsteady interactions like BVI. If I look at broadband noise, right, this is the interaction with turbulence with the blades, and then we can model that pretty easily. That's really a form of unsteady loading noise, if I think about it in that way. And that actually, because it's that time derivative term is now actually driven more by the fluctuation of the source than it's driven by convective amplification. That in fact does not decay very much with reduction in tip speed. And for self noise, right, the noise of the boundary layer of the airfoil, at some point as I start to slow this rotor down, well, the angles of attack are going to get pretty high. And I'm actually going to start to increase the thickness of the boundary layer, even get to separation, and the noise will start to come back up again, right? If I had unsteady loading, say to do some sort of aerodynamic interaction, it might not come back up again, but it could level off, right, depending on what's happening. It's going to change or decrease very slowly with tip speed. So the one thing is up to a point, right? Tip speed reductions for these vehicles are not going to get me out of my noise problem, right? Particularly, and we see this a lot somewhere in this region, 0.4 to 0.5. I'm probably going to stop seeing very effective benefits from tip speed reduction. And I think it's no coincidence that a lot of the kind of more well-developed eVTOL vehicles we have today live in that range. And like I said, there's complex configurations. Try to get this going. Okay, sorry about that. Right, so here's just some images. These come from Continued Dynamics we're working with on some projects that just show sort of the these lines that represent the vortex wakes for a couple of different vehicles, one that's sort of notionally like the HANA, another that's like a lift plus cruise vehicle. And we can see there's lots and lots of new opportunities for unsteady aerodynamic interactions that are sort of like BVI, right? So I can have interactions between the tail and the propeller, rotors and struts, the wings and the rotors, rotor in the airframe, and of course, rotor and other rotors. So there's lots and lots of potential for aerodynamic interactions that themselves are going to be sensitive to operating condition. And again, as Rajneesh had mentioned in his talk, right, one of the benefits here, though, the opportunity, is that these vehicles tend to be over-actuated, right? So they've got more controls, really, than are necessary in order to define how you fly along a particular trajectory. So we have lots of opportunity to change the aerodynamic performance of these vehicles by changing the configuration adaptively, but also to affect the noise. And to give you sort of an example that we have good data for, right? This is just something like the XV15, right? So it's a tilt rotor. And over here on the right are some acoustic hemispheres that I've plotted. So they show, again, noise levels as a function of directivity for if I have the nacelle at an 80-degree angle, so close to vertical like a helicopter, and I get this large increase in impulsive noise that is radiated ahead of the vehicle. And then if I move the nacelles down to a 60-degree nacelle tilt angle for the same 70 knot, 6-degree descent flight condition, that noise goes away almost completely, right? Noise in other directions isn't really effective. So, I may be able to tailor where the noise goes and control it by changing or taking advantage of this fact that I can non-uniquely trim the vehicle. There's lots of ways to trim it to do the same thing. On the other hand, right, those benefits may be limited. They may be limited to certain directions, and they could certainly harm performance. Look at another example here. So this is a study we've been doing. This is a project I've been working on with Ken Brentner here and Joe Horn, who does a lot of flight dynamics work and simulation. And we've done some simulations here with a generic distributed electric propulsion vehicle, lift plus cruise. And just give some parameters about it. But what we're going to look at here is a noise prediction that we'll do with a couple of different flight control schemes. So we're going to do one flight control scheme that's been programmed such that we have a variable RPM, which is used for thrust control on these 4 lifting rotors, and another flight control scheme where we're going to vary collective pitch predominantly. And even in that case, like the rotors are not phase locked, they still can kind of vary a little bit, but collective pitch is largely what's being used. So I'll just show you one example here, right? So this is going to be a very mild maneuver. So we're in transition. The rotors are doing, we're only going at 10 knots. That pushing propeller in the back is not doing much work yet. And we're just going to do a 5-degree roll angle doublet. So we'll roll to the right 5 degrees, and we'll roll to the left 5 degrees, right? And, or sorry, the other way around, left first and then right? And this is like a plot of the trajectory that you can see, right? So it's just a mild little perturbation of the vehicle. And over here, we just have, shows you, say, the change in pitch or the change in RPM, or not RPM here. Yeah, these are the flight state, sorry, the roll for the vehicle. You can see the variable pitch and the variable RPM control schemes both track the same trajectory pretty well. Here we go. Here is the plots here that show now on the right-hand side over the course of this trajectory, how we have the change in RPM for the variable RPM case and the change in pitch for the variable pitch case. They both change in sort of similar ways, right? Because we're really using them to manipulate the thrust on the rotor. And I want to point out here, though, if we look at the noise levels that we see at different elevation angles, these are different angles relative to the vehicle, we see that especially in the plane of the rotor, we get a really large increase in noise due to this use of the rotors for control for the variable pitch scheme. And there's a lot less sensitivity for the variable collective scheme. And the other thing I want to point out is you can see there are these spikes in noise that right where the doublet starts and where it ends, right where each of these sort of submaneuvers start. And that really has to do with how I set the gains in the flight control system. So it doesn't have to be like that. If I were willing to accept a little less tightly tracking trajectory, I could probably reduce noise a little bit. So that tells me right there that there's a lot of work to do in terms of how can I design the control system in such a way that it's going to minimize noise. Another thing that I kind of wanted to point out as we get close to the end, so this is actually work that was done at NASA by a colleague of mine there, Kyle Pashoni. And this is this consideration of the rotor phase angle, right? So this is basically the angle around the azimuth that each rotor is at any instant in time, right? So this picture cartoon up here shows something for he did some things for predictions for the GL-10. That was a NASA vehicle that has 10 rotors, so it's a tilt wing. 8 in the front, 2 in the back. And he's just in this cartoon, all the rotors here on the left are at a, say, 0-degree phase or azimuth angle, and all the rotors on the right are at a 60-degree phase or azimuth angle. And these plots down here show ground noise contours for the vehicle. It's in the center of this plot and it's traveling toward the right. For different combinations of these 0 and 60-degree and some 30-degree phase offset angles. So you can see just by changing the relative phase between these vehicles, I actually make quite a dramatic difference on what those patterns of noise look in the ground. Because in some directions, right, those the acoustic waves that are radiated to the rotor, they're going to add coherently, right, and then they'll all get an increase in noise. In other directions, right, because of the time delay it takes for the acoustic signals to propagate, right, by changing that phase angle, I'm going to get cancellation. And that's going to cause the noise levels to reduce quite dramatically. And of course, if I have a randomized phase, I'm going to get a very complicated pattern here, which may or may not be favorable. Right, and that's probably what most vehicles are doing today when they're not trying to control phase. So you can look in a similar way. Maybe this is an opportunity. Maybe I can try to control the rotor phase relationships in such a way as to reduce noise on the ground. So Kyle did that. And here's a good example here where he's applying these things and then optimizing essentially to figure out what rotor phase combination can I use to reduce the noise in that black dashed triangle, right? So different quadrants essentially of this field. And you can see you can very effectively, even in 2 dimensions, sort of reduce noise. So you could point this cone of silence, where you have a noise sensitive area. And then maybe on the other side, I've got a river or a highway or something like that. And I can sort of, live with the fact that I maybe am increasing noise a little bit in those directions. Now, the question is, nobody's tried to put this on a real vehicle yet. Can I have some control system that maintains these phase relationships while I'm still providing adequate flight control for the vehicle, right? And that probably gets easier the more over actuation I have, but it may still have some flight control performance and handling qualities benefits. That's an area that I think we need to look into because the promise is so great. So I just wanted to kind of wrap up here by kind of talking a bit about the good things and the bad things I hope we can get out of this, right? Idea of acoustically aware flight control, right? So the benefits, and I hope I've been able to convince you of, at least for the work we've done on helicopters, is that we can get really significant reductions in noise by having tailored flight operations, right? The rotor noise is so sensitive to how that rotor is operating that there's a lot of control you have on it, even after you've built the vehicle. But I think those kinds of operations are only possible if you really come up with them at the time of use, right? You need to be specific to that particular operation. And I think the way to do that is to leverage all the advances that are happening right now in autonomy, right? Instead of putting this all onto the pilot to handle, we want automated systems that are aware of the noise that's being put out and help the pilot balance kind of trade-offs between noise and performance, and hopefully in some cases there isn't one, without really adding a ton of pilot workload, right? You want almost like back in the old show Airwolf or something, where the pilot has a knob between like quiet and efficiency or something like that, and that's as far as they need to worry about acoustics, right? What aspect should I emphasize at this point in the flight trajectory? The challenges that we have to getting here, especially for these novel vehicles, is that we still lack a lot of data that we need to validate and understand the kinds of models that we're trying to put together. So I'll give you a couple examples here on the right. This is certainly a problem we're trying to tackle. Lots of other people are trying to tackle it too. But we're engaged in taking full-scale measurements of UAM and UAS type vehicles right now, so we can understand what these things actually do during the operations they have. So it's a picture of Beta's Aliyah 250 lift plus cruise vehicle flying over our microphone array. Down here in the lower right, this is some lab scale studies that we're doing, right? Where we have a multi-rotor test rig. We can actually orient these rotors in whatever orientation relative to each other we want and take a look at rotor-rotor interaction noise in this anechoic chamber, anechoic wind tunnel really, with an array of microphones. Of course, then we want to use the physical understanding that we gain from those models, or from those experiments, to develop low noise models, and that's something that we're working on. So this is some we mentioned we're really interested in noise generation by turbulence, right? So we've got some aeroacoustic codes tailored to rotor noise turbulence or rotor turbulence noise prediction. This one's called Album. And also then we want to do this on-demand planning, including multiple aircraft, right? The entire airspace. What's the effect of I can't have every vehicle kind of deciding on its own where to fly. They need to coordinate together to have the minimum acoustic benefit and the most efficient air transportation system possible. So this is kind of an integration, just a picture that shows the integration of our noise model into an unmanned traffic management tool developed by a company called OneSky. So that's kind of all I had for you today. I want to thank you very much for staying up and listening to this. And I'm happy to use the time remaining to answer any questions. Thank you.
Thank you so much, Dr. Greenwood. It was a really amazing presentation and a real eye-opener for me, actually, because my understanding of noise has been very limited. Frankly speaking, I always used to think that, so I remember Professor Leishman once mentioning in his class that rotor noise varies as some function of tip speed, and it increases. So that's what is still stuck in my head. And the plot which you showed, actually, that was really remarkable and amazing. Where at a point, so you have a sort of a bucket where your noise is lowest. That is it's coming as a shock to me actually right now.
And I'll be honest, that was initially a bit of a surprise to me. And the first time we saw this, I've been working with Mobile Benedict, right? We've been working on this Go Fly competition, and we're trying to develop a really quiet helicopter. We started doing some preliminary design type noise calculations for that, and found that, eventually you tip speed reduction stopped getting you anything, and it could hurt you. All right. And I think a lot of the eVTOL companies have figured this out too, because like I said, when you kind of suss out what tip Mach number they're running at, they're all running somewhere in that bucket.
So, is there any, if you could just comment on the basic physics, I mean, like what is actually making that happen? I mean, of course, you showed the elements which are there, but for a layman, I mean, like students, I mean, who may not be able to appreciate all the different components you talked about.
Yeah. So really, what's happening there? I kind of talked about, and there's some different perspectives on how you look at this, but we talked about like thickness and loading noise being the main sources.
Right.
And thickness noise, right? The noise that we associate with helicopters, largely the thickness noise and kind of the steady components of loading noise, that is entirely driven by the tip speed. So as the tip speed goes down, that just drops right off. Now, in the loading noise term, though, right, the other way I can get a time rate of change of the loading noise is by having fluctuation at the loading itself.
Right.
And for and that's not going to drop off the tip speed, right? That's what driven by the aerodynamics. And for the broadband noise in particular, right, that's going to be driven by the unsteady pressure perturbations that are caused by having a turbulent boundary layer. So as I reduce tip speed for the same rotor, right, in order to generate the same amount of thrust, I'm going to have to increase the rotor angle of attack. And as I increase that angle of attack, my boundary layer gets thicker, gets more turbulent. Eventually I start to separate, and that causes more unsteady pressure perturbation fluctuation. So that's in that particular curve. The reason why these broadband noise sources start going back up is I really am overloading or trying to get a lot. I'm still far away from stall, but I'm really trying to get a lot out of that rotor, right? I'm operating pretty close to its limits.
So thank you for the explanation. So I'll now go through the questions which people have asked in the chat. Yes, so the first query is from Dev. He says that most of your studies are, which you talked in the presentation, are actually more on the external noise, the noise which the people outside are going to perceive. So what about the noise which in a UAM, there are people who are sitting inside the vehicle. So what about them? What kind of noise are they perceiving? So if you want to comment on that.
So that's a great question. It's a little outside of my expertise. Certainly it's driven by the same noise mechanisms that we have for external noise, or at least in part. There could be other things like, and one of the big things is that when I'm doing an interior noise prediction or modeling, right, I have to worry a lot about the structure of the vehicle, right? Because, there's two paths. Either I have vibration that's happening actually at the rotors, right? And that vibrates through the structure, or I have acoustic waves that come from the rotors and they hit the body and then they cause the structure to vibrate. And then typically that structure, the vibration of the structure, like flat panels in the structure and things like that, they act like a drum head. And I get secondary acoustic radiation, and that's what you hear inside of the vehicle. So what I'll say right now for a lot of these vehicles, in terms of internal noise, is people are pretty far away for the most part of having revenue generating passenger flights. They're trying to keep these vehicles light, and that means that they don't have a lot of room to put in extra damping, acoustic treatment inside of the vehicle. And I've had the inkling talking to people in the industry that they are all getting a bit worried about internal noise, because if you've got this trade-off, right? Once I've solved the external noise problem, well, if I want to reduce internal noise, I probably have to make my structure heavier. And especially if I'm using batteries, I can't afford a lot of extra dead weight. So,
okay, good, thanks. Next question is that for a given fixed environment, say city area, fixed buildings and all, the problem kind of boils down to training the model using reinforced learning. So the question is that actually, did you look at reinforced learning as an alternative to A-star and those kind of methods?
Yeah, so I've done quite a bit of work with different approaches for machine learning that have been applied to rotor noise prediction. And in terms of noise levels. And then a lot of the other work we've done is actually this kind of idea of maybe I should combine a physics-based model with experimental data. So if I have some physics-based model, then maybe I can use experimental data to calibrate that model, and I can use a machine learning approach to do that, and that's proven pretty successful. Now, where all of this starts to get a little dicey for us is we start to move to these multi-rotor vehicles, right? So I told you kind of there, I've got this single rotor, and its operating state is a function of 4 parameters, right? So if I have a machine learning model or something like that, when I want to build, I've got 4 dimensions, right, that are going to govern that, and I have to find data over those 4 dimensions sufficient to inform that model. If I have 2 rotors and they're interacting with each other, well, I have 4 parameters for each of them, but then I have all the couplings, right? So probably like 16 parameters now, right? And imagine if I have a 12 rotor vehicle and they're all coupled together. I mean, it's like 4 to the 12 powered parameters, right? So I have to do some kind of model reduction. And I think we're not quite sure yet what the best way to do that is, right? That's kind of the sticking point for that kind of fast modeling.
There's another question regarding, I mean, if you have any suggestions for commercial and open source software which could be used to look at aerodynamic noise and predict.
Sure. Yeah, I can put in a plug for, so it's not open source yet, but PSU WOP. We will give the binary away to anyone who asks for it. So there's a request site, and you're welcome to email me, and I can send you that. And we have some open source. Okay, good. So we have some open source tools that are written in Python now that work around it. So you can sketch up a rotor blade in OpenVSP, and you plug it into this tool. It does a little aerodynamic analysis, builds all the WOP input files, and gives you some max output. And WOP itself, we've kind of moved internally to an open development model. And we're just trying to sort out a couple of kind of bureaucratic issues here, but I'm hoping in a few months we will have that code open source as well. And we really welcome contributions, and we want to know how everybody else uses this so we can make it better.
Absolutely, absolutely. That would be really great, actually. Next question is regarding, since there is a direct relationship between the intensity of noise and the strength of the vortices, could it be said that the noise is directly proportional to the thrust of the rotor or the disk loading?
So that's an interesting thing. We did some studies here looking at that kind of thing. So I'd say yes. To first order, you would think like if I doubled the thrust, right, then all the loads are going to go up by a factor of 2, and I run through Fox-Tom's equation, I get a 6 dB increase in noise, and that's approximately maybe to first order kind of true for an isolated rotor. We have looked at this for helicopters though, right? So I say I have a helicopter going descent path, and the problem is if I change the thrust by a little bit, or the thrust coefficient, I should say, so maybe I change air density, the helicopter is going to trim out in a different way, right? So I'll have to put the drag in the fuselage, I'm going to have to put different controls in there, and I end up changing things much more dramatically than you would think. Right. So, initially we in the acoustics community had kind of thought like it doesn't really matter what payload you put in the vehicle because, it takes a factor of 2 to get only 6 dB of change. It's not that much in the noise community. But it turns out, it's much more sensitive to that. A 5% change in the vehicle's weight can change dramatically how it trims.
So then the same line, I mean, there's a question regarding on how high or low would the noise from a Black Hawk rotor be compared to a V22 rotor or an F-35 lift fan, since all these are having very different disk loadings? And
yeah, so I did a lot of measurements of military vehicles. I know those answers a little bit precisely, and I'll just say like loosely, certainly something like an F-35 is going to be very, very loud for the same thrust. Say like a V22 in hover operates at a very high tip speed. So it's going to be quite loud in hover. Not so much maybe in forward flight because the tip speed actually gets reduced. That's one of the things that happens. So that's a sort of a general order of magnitude. So it's actually, this kind of goes back to it too, like people complain a lot about helicopter noise, but if you were to look at like a turbofan engine from an airliner that produces the same amount of thrust that a helicopter produces to lift, right? The turbofan makes much, much, much more noise. It is enormously louder, right? And people don't complain about that because they're at the airport.
Yes. That's a really valid point. I mean, actually, I never realized that because you're inside the cabin with all that thing. So it's an interesting thing to know as well. Yeah. There is another question regarding, are we looking at changing rotor RPM to reduce noise when we are moving to built up areas and communities and so on?
Yeah. I think absolutely. And then that's actually one of the big advantages, say, for these electric propulsion type vehicles too, is the rotor RPM can very easily be varied depending on the flight mode that I'm in. right? So if I think almost all these vehicles, if I'm on hover, I'm going to have a very high RPM, just like the V22 does. And then when I get to forward flight, I'll slow those rotors down because I don't need them to do so much work.
So there is a question on, in the GL10 design, what would be the main factor that led to the choice of 60 degrees as the phase difference between the rotors to eliminate noise?
So I think that just relates to the fact that there's 3 blades per rotor, right? And that's so I've got a kind of 360 divided by 3, and then I take halfway between that. I think that's the only logic there. That paper that I referenced does a lot of other combinations. They look at random variations. They look at different synchrophasing. Ultimately, like it's like a phased array. So if you look into phased array processing, right, I can figure out what phase that I need in a particular direction, and I can actually steer it, right? So if I change the phase relationships between, even if I have 2 rotors, I could shift the noise around from canceling directly ahead to off to the side. So it ends up kind of just being a minimization problem in that sense.
So continuing to the same question, is there a phase difference value that would work in a similar way that would work on 2 rotor systems like coaxial, tandems, or tilt rotor? Would it be different for all these configurations?
So yes, and that's something that people have looked at. So you could imagine, these guys have, they have cross shafts or something that are connecting the rotors in those cases, but I could choose a particular phase angle that I would want to put those things at for noise. You can do that, and there are certain combinations that are actually going to minimize certainly noise in different directions, and they actually maybe minimize the acoustic radiation efficiency, right? So how much of the power that the rotor is putting into the air gets actually transferred into noise. You may be able to minimize that by picking certain combinations. However, I'll say, I think most of those combinations are picked by some combination of either aerodynamic performance or vibration in the vehicle. And probably for something like the V22 or the Chinook, acoustics are not factor number 1. So those things are going to win.
Right. So I think it's the last question in the chat box. What is the effect of shrouding a rotor? Can that help in reducing noise?
So that's a good question, and I'll say it's really complicated. So people, I think, assume that you always win from a noise perspective when I put a shroud on there, and it's not true. So the shroud can help you in a sense by scattering, blocking the noise from escaping. And in fact, if I look at a turbofan engine, right, they have these big shrouds over the fan, right, and the fan has lots and lots of blades. So the shrouds are actually very, very long compared to the wavelength of the noise. They mostly work by having this cutoff phenomenon. So there's actually a lot of acoustic energy that cannot leave the duct, right? It's just the modes, and you can look into these like helical modes of sound. They don't get out of the duct. They stay in it, right? So that really reduces the energy, and then they put in acoustic liners, right, to further attenuate the stuff that's near that cutoff frequency. So anything that is just on the edge of coming out, they'll try to absorb it inside of the liner. From a lot of these VTOL concepts, we're not going to have a shroud that's multiples of the diameter of the rotor because it's too heavy, right? So the shrouds start to get smaller and smaller and smaller. So they often don't have enough depth to do much in terms of acoustic performance, maybe a little bit in the plane of the rotor. And then the other kind of factor that you have to worry about is, like we talked about, so much of this noise, especially if I have a low tip speed, is based on an unsteady aerodynamic loading. So if my duct, say I'm trying to push it edgewise, generates a lot of inflow distortion, and then that's going to cause a lot of unsteady loading as the blades pass by. So I can lose acoustically if I have this duct in a condition where the duct itself is generating noise. So it's really a balance. There's some tricks people are working on. Maybe I can put like resonator tubes and things inside of my shroud to make it more effective acoustically, but it's tough. It's a tough problem, and it's not a guaranteed winner for acoustics.
Actually, on the same lines, I remember having a brief discussion with Ben Berry once. We are talking about, which different configurations are good or bad, and I was kind of favoring Lilium jet. And he was very quick to point out that Lilium is not showing actually the kind of noise those ducted rotors are generating. So most of their videos have music in the background, and you don't get to hear what exactly those 36 ducted rotors are actually generating.
Yeah, I'll say this. There's a video recently that Lilium released from their 4th flight test where you can hear it. And I will say, so their ducts are actually long relative to the rotors. And when you hear it, at least whatever you can hear through the YouTube video, it mostly sounds broadband. So I think they have done a good job of reducing the tonal noise. I was a little surprised too, because I was a bit skeptical. And you see they have things, and I thought they were just for looks initially. These chevrons near the end, so these kind of ragged trailing edge. You see this on some Boeing airliners now, right? And that helps reduce the mixing noise from noise that's coming out due to turbulence coming out of the back of a jet. Maybe those actually do something on that vehicle. So it was very interesting to me. So. But I agree, it's not the quietest vehicle, I don't think, based on what we know so far.
Okay. I think one more question has come up, so this will be the last, hopefully, and we won't be keeping you for much longer. So this is for urban UAV transport. Can we see use of ground electric power instead of fossil fuels in the place of onboard battery? Okay, this is actually off the topic, kind of. Okay, this is actually a separate question altogether. I think we can ignore this question, not related to your presentation. This is probably for the last presentation. So a bit different. So I think that is all from our side. Okay, there is another question. Okay, will variable rotor blade, so variable geometry rotor blade help in minimizing noise? If we have a morphing rotor.
Yeah, potentially. Right, so potentially. One of the things that you could maybe think about is certainly if I had certainly depends how I'm going to do it, because some of these rotors that are variable RPM are fixed pitch, right? So if I had active twist or something like that, even if it's slow, right, I can tailor things so I can keep the RPM down in certain conditions. And then, if I had like a variable diameter, some people have looked at, right, I can do some sort of the same sorts of things where I'm balancing what do I need for hover versus what do I need for high speed forward flight in order to keep tip speed down. I'll also say there's a lot of work on passive blade shaping. So if I have a blade that's going to pass by a structure or a turbulent eddy, right, I can shape it in such a way, it kind of works a little bit like those chevrons where I'm trying to break up the coherence of the noise so that it doesn't focus in one direction. Like the Eurocopter Blue Edge blades, if you go and look up that thing, they've got this kind of dog leg shape at the end of them. That's to break up the coherence of BVI, and it's effective, right? And that costs you very little. So that's a promising approach, I think.
Thanks so much. Okay, so I thought it was the last question, but one final question there for Foley. So relation between the noise frequency and rotor RPM, and also dependence on the number of blades.
Yes, exactly. So all the tonal noise for the rotor is going to be a function of the blade passing frequency. So it's the shaft order rotation times the number of blades. So if I add more blades, the frequencies go up. There's I'll add a little to this because it's a thing people don't always necessarily realize. Right, I'll get noise that occurs at all the harmonics of the blade passing frequency. And you go, if I have a 4-bladed rotor and I started with a 2-bladed rotor, right? And I'm comparing the two. When I go to a 4-bladed rotor, where did all the Tupper of noise go? Right, and it's because it gets canceled out. Right, those extra blades literally cancel out the noise, so there's less acoustic energy in those lower harmonics. So that's a benefit. The downside is some of these things, especially once I have interactions like BPI or something like that, I'm increasing the frequency at which they occur. And that can, I might have less energy, but it's more annoying. So there's a trade-off there, right? So that's kind of a balance, again, that you have to pick based on the situation.
So yeah, I think that is it in the questions. And thank you so much, actually, for spending so much time and answering really so many questions which came across. And I would also like to thank all the people back in India, who are probably skipping their dinners to listen to you and stay awake till this time. So it was a really amazing lecture. So thank you so much. And I'll definitely connect back to you to getting the software which you mentioned. Please you walk whenever it becomes available.
Great. Excellent. Thank you very much. It was a pleasure. So take care, everybody, and have a good night.
You have a great day. Bye.
Bye.